Thank you for coming. Can you hear me clearly up there? Looks like it. So I'm going to talk a little bit about virtualization and in embedded. There'll be a bit about, well, quite a bit about Xen as well, but I'm going to look at other open source hypervisors as well. But first, actually, we have to ask ourselves, why do you want to embed virtual systems? And to a large degree, it's actually quite similar to server virtualization. It's to one degree about consolidation, which primarily is about cost, size, weight, and interestingly, in some cases, also about heat and so on as well in an embedded context too. I think there's a few examples, for example, like in some car environments, like when you have the little camera which helps you park and stuff like that. That can cause some problems in some areas with heat because you have a few CPUs in very close proximity, which has to be somewhere in a car. So there's additional aspects to this whole thing as well. Another interesting thing, which is particularly interesting in the embedded context, is also about, to some degree, reducing the development cost, i.e. being able to port legacy applications or something, which you've written to a different environment without having to do all the base porting work because you're working towards in a virtual environment. It's also around security and safety can be big concerns in that space. So one thing which you typically want to do in an embedded environment is to support, this is called mixed criticality compositions, which means you want to be able to run applications in different containers, if you want so, with different safety, security, and real-time requirements. One of the key things in some markets is you have to have a safety-certified hypervisor if you use a hypervisor technology for isolation. And then you have a whole set of additional embedded requirements, such as low interrupt latency, lower zero scheduling overhead, particularly if you do something with rich I/O, which is quite often the case for, say, automotive applications. You need to have a lot of drivers for specialized I/O, touch screens, all these kind of things which you normally have on a phone. And to support all this, you need to have a fairly flexible architecture to build, widely varying systems, if you want so. So let's just really do a quick reminder of hypervisor architectures. I'm going to focus on ARM only because that's sort of the main player in this space. So if you look at ARM privilege layer levels, you have EL0, which is user mode, EL1, kernel mode, and then you have that EL2 space, which is where a hypervisor would run in. And then underneath, you would have something like trust zone as well, and there's some interactions, between trust zones and hypervisors too, but that's going to get a little bit complicated, so I'm not going to go into this. So how does a hypervisor, how would they typically map into this model? So your classical type 1 would run in EL2. You would have your drivers run as part of the device, the hypervisor. Then you have all your virtual machines sitting on top of it. Then you have this type 2 kind of model where you have fundamentally the host kernel and the hypervisor kind of run together. Like if you look at KVM, the hypervisor is kind of KVM-IO kernel module. Then you do have this whole user space, box which comes with the host, and then you have your, VMs there. And what's interesting, if you look at it from a control plane perspective, in the model on the right, you kind of can just use the user space of the host for control, whereas, typically what you would do in a model on the left is you either have some kind of interface where you externally control the whole system, or you have some bit of code as a module in there, or you use one dedicated VM to do that. So let's just look at a few examples of hypervisors today in that space. So there's one which is kind of really interesting. It's called L4E. It kind of comes from a wide heritage of hypervisors. There's a whole family called the L4 family. Kind of originally were developed for the whole mobile space. This one keeps on coming up in discussions about automotive. It's written specifically for mixed criticality compositions, a typical microkernel design. In the kernel space, really, they just do address space, implementation threads, and IPC kind of functionality. Everything else is in user space. It's got a solid feature set. I think it is a little bit weak on hardware support. It's also kind of arguable, particularly at this audience at FOSDEM, when it's really open source. You know, it is GPL, but it's got a dual license, and you have to sign, you know, do copyright assignment and all this kind of stuff if you want to contribute. Also, there seems to be no real community around it. But, you know, this could go somewhere. Another one which occasionally comes up here is Jailhouse. It's relatively lightweight, less than 10,000 lines of code. It's a partitioning hypervisor. It comes from Siemens. Community-wise, relatively small. I think 80% of all the code seems to come from one developer. They use Linux to kind of bootstrap the system, and then after the bootstrap, it's kind of, you know, still partly used for control plane. The focus there is really on partitioning, but not so much on virtualization. So they don't have things like scheduler, you know, I/O emulator and stuff like that. It seems to have a really good basic feature set, but there's some areas which are, you know, still under development. I think particularly because we're talking about ARM virtualization here. You know, the ARM 64-bit support is fairly new. There's also really interesting talk from the AGL, which was given earlier this year, which you can get to. The previous slide has a similar, more in-depth discussion here. Then we have Xen, fairly, you know, general-purpose hypervisor. Most people know it from cloud computing and basic server virtualization, but as we will show, it's actually used in a lot of other market segments today too. Again, you know, we have Linux and NetBSD to bootstrap. It's got quite an expensive feature set. It's highly customizable, and we have a fairly strong and diverse open source community around it. And the following picture kind of gives you a sense of this. Well, this just shows, you know, like different vendors having built products and services around it. If you look at the top right, that's sort of traditional server virt. Then we have kind of cloud computing. Then the top left bottom, that's kind of security-focused products. And we'll kind of go a little bit into this because security is a big aspect of the whole embedded story as well, and then we do have quite a few embedded products as well. And actually, I started working with Xen around 2011, and really what happened is that whole security segment started to pick up around that time, and it's grown since. There's been a push which doubled the number of players pretty much in the last 2 or 3 years, which was around that time when all this embedded stuff just started happening. We didn't plan for it. It just happened, you know, basically because there seems to be a good match for it. So let's draw this back on. We talked about hypervisor architectures before. Let's bring this back to what is actually Xen, because, you know, it's kind of a type 1, but it's kind of not a traditional architecture. So one of the differences between your traditional type 1 and Xen is that the device drivers don't run in EL2 and not in a hypervisor. We basically reuse the drivers from DOM0, and then basically because we have the specialized, you know, DOM0 virtual machine, that's then also our control plane. There's strong isolation. So, for example, the drivers are running in EL1. As I said, in the L4RE, they're running in user space, so that's obviously a little better. And then we have these grand tables which kind of provide additional isolation between different VMs. From a control plane perspective, you know, on a server system, you know, the sysadmin will basically, you know, use DOM0 or some graphical tool, you know, which connects to it to control your system. In embedded, you need a lot less. It's really, primarily used the control plane for config and setup, and then basically primarily for system health monitoring, applying possibly software updates and those kind of things. So you need much less functionality there. So having a big distro running Endom 0 isn't really necessary. So what people in the space tend to do now today is just use a basic Linux kernel with a root file system or something like that. But this could be made smaller, and there's some work going on in this area. And that shows you the control plane. So let's talk about so we talked about some of the specific requirements in embedded. And one of them was around PB drivers, which is I/O and so on and so forth. So there's been quite a lot of momentum in our community for a while. So we have all this standard stuff around disk and so on that's been around forever. There's also some GPU sharing. It's not traditionally a PB protocol in the way how it kind of works. It's a slightly different model, but it has the same kind of effect. There's also work going on, and this is being driven by some automotive vendors around general coprocessor sharing, so that taking some of the ideas we used for GPU sharing and extending them to FPGAs and anything which might kind of look like a coprocessor because it's the same kind of principle. Some prototypes around there right now. They've made some design changes recently, and we'll probably have a fully baked framework come this year. Then there's been quite a few new ones. There's a 9PFS PB cores, that's sort of POSIX forward, call forwarding, where you have your POSIX API in one VM, and then you basically just have a shim, and it routes calls through. It's actually quite interesting. There's been benchmarks as well, and there's things like multi-touch, sound display, DRM. And what's really interesting, and I find this a lot of the embedded companies, they just tend to, embedded companies, they just take stuff, they hack it, and then they push it out. And so we found that a lot of them, are writing their own drivers. And a couple of them I managed to get them to upstream it and standardize, which is kind of good, but it's relatively easy to write those drivers, particularly if you don't care about standardizing the ABI, which you can do if you do this for your own product. So let's look at some security properties of Xen. Security is kind of important. So apart from the typical hypervisor functionality, you have functionality which enables you to do further system partitioning. So, we already touched on this. You can basically disaggregate your system in Xen, so you can run device drivers, in a specific VM. Network drivers are typically a main route of attack for a system. And you can do this for other drivers as well. You can put other system components into separate VMs as well, and then kind of plumb it all up to make a distributed system. There's also the capability of controlling the capabilities of a specific VM with the Xen equivalent of SE Linux. And that kind of enables you to build a multi-layered security approach, and that's actually being used in some of those products, some of the security products which started appearing a few years ago. There's other security features like trusted execution environment and stuff like that, virtual machine introspection, L2PM live patching, all this kind of stuff, but it's not quite clear whether that's interesting for that whole embedded segment. I mean, I could imagine that virtual machine introspection could be something interesting for health monitoring of a system, but it's not quite clear how this would fit in. As we're talking about security, I think we do also have to talk about Meltdown and Spectre quite quickly. I don't know whether we had lots of talks about this yet today, but obviously Meltdown is the most dramatic one. From a Xen perspective, it can't really be exploited in fully virtualized VMs. So fundamentally on ARM, we don't use software virtualization, we just use hardware extensions. So from that viewpoint, we're actually fine. And on x86 with HVM and PVH, that's true as well. We do have mitigations, but I think for that embedded and automotive use case, we don't have to deal with the performance overhead some of those fixes will give us. Spectre is a lot more interesting. We started going through the code base at this stage manually. Hopefully at some point tools like Coverity and stuff will help us find some of the kind of gadgets and code patterns which could be used to exploit those vulnerabilities. But it's a lot harder to kind of go down this route in an XN-based system because, to exploit Spectre, you need something called a gadget. So in a Linux kernel, there's this eBPF engine, which was, by Google Project Zero used on KVM to demonstrate how you get information out. We have gone through the code and, not line by line, but through the architecture, and we don't think there's anything similar to that in the code base. But at the end of the day, we won't really be sure unless there's really tools which allow us to verify that. So hopefully that should be fine. Let's look at one of the other techniques. So there's this whole sandboxing disaggregation thing, where you can run drivers in different VMs. So how does this work? Well, you have a regular, your DOM0 on the right, a regular application running in a VM, and then, we have this thing called a storage domain, which would have a disk driver in it, or a network domain, which has a network driver in it. And then basically, DOM0 kind of connects to topology, and your application will talk to the back end, which will talk to the front end, which will talk to the back end in the storage domain, which will talk to the real disk driver, and it would then talk to the controller, and the same can be done for network. And fundamentally, the same can be done for any I/O pretty much. Then there's this thing called XSM or Flask, which is like a XM's variant of SE Linux. So here you have your VM. You write the policy, which controls what you can do with various interfaces. So you would typically define some classes of VMs and then assign those classes to specific workloads in VMs when they come up. That gives extra protection because then you can only do certain things, certain operations from within this VM. Everything else gets blocked. It's disabled by default, so you do have to enable it by kconfig. And it's very similar to the Linux security modules. It uses the same policy syntax. You can use all the same tools. It's just different new objects which are used on top of it. And fundamentally, the guys who do that use XSM together with SE Linux in their systems. If you want to know more, there's a little bit of documentation. The slides will be online via the FOSDEM site and also on my SlideShare channel. So that's some of the terminology around security. So I kind of want to look a little bit into how this actually works. So we have a number of security-based products in XM. So there's CubesOS. CubesOS, they have a booth here at FOSDEM. Go find them if you're interested. There's OpenXT, which is in some sense similar to CubesOS. It's just an open source project which allows you to build CubesOS type of applications. And then there's a product called Crucible Defense from a company called Starlab, and they're targeting military type applications. It's kind of certified product and so on and so forth. So I wanted to briefly show how some of the stuff works in practice. So CubesOS, Edward Snowden likes it, which is probably a good thing. And how does this work? So you have your typical Fedora UI here. On the top right, you see kind of all the VMs are running, and then on the left, you kind of it's like an application starter, like on Windows, where you can basically define which application runs in which VM. behind the hood, you have Xen, the DOM0 kind of does all this UI stuff. There's a network domain. We have a firewall VM which controls all the firewall policies. There's something called a USB service domain. When you put a USB device in, that gets started in a VM, and then you have, those defined different VMs where you run different applications in. And if, for example, you then start, an application, then like your network traffic would be routed through those VMs, and then your USB traffic would be routed through that. So you kind of get this extra isolation, which makes it harder for exploits to infect your entire system, because you have all these little sandboxes in place. And they're going down some interesting routes of being able to host some of this in clouds as well. So go talk to them if you're interested in this. So embedded in automotive. One of the interesting things is being able to partition a system. So in Xen, we have a lot of different schedulers with different properties, and you can assign these schedulers to different groups of CPUs on the system. This shows we have an ARINC scheduler, there's a hard real-time standard, there's a soft real-time scheduler, we have a regular VM scheduler, and then there's the capability to pin virtual machines to CPUs without overhead, using the entire management stack. So that kind of doesn't give you a lot, it does give you still those virtualization boundaries and all the tools, but it's a very attractive proposition. Here's the same thing again in terms of overviews. I'm not going to go through this in a lot of detail. Have a look at this later on if you're interested, or talk to me afterwards. Another interesting property, this is around interrupt latency. So we have this concept that interrupts where physical always follow virtual interrupts. So when an interrupt gets injected, it's always injected on a CPU, which is running the virtual CPU. If for whatever reason that is moved by the scheduler, then at one point that gets routed back to the other virtual CPU, and the next time around it comes in the normal way. And what's interesting is that actually that whole approach really gives you fairly low interrupt latency and this was around 2,000 nanoseconds with the null scheduler, and that's the sort of maximum over a specific run, and there's a whole blog post about that too. I think one of the things we do need to talk about, particularly if you talk about automotive, is safety certification, because that's a big, difficult issue in open source. So there's several levels to this. So one is around code quality. You typically would have to run special static analysis tools, which are quite expensive, which where you have to comply to the cert MISRA coding standards. We've been running a project with a tools vendor who's been doing this for us for free, and we're starting to work through the issues. So that's kind of a good first step. Another thing around certification is you have to prepare a lot of artifacts all the way through the development process, from requirements all the way how it gets implemented in the code. This is kind of tough in an open source project because it's a lot about reverse engineering. We have had 2 companies who have done this, so we know it's doable. So it's, at the end of the day, it's just a cost thing. But then those guys, of course, have a commercial project, and they pass it on, they pass the cost on to their customers. And you kind of lose some of the sharing stuff around open source. Development process is thorny. Open source development process does not comply with safety standards. There is a way to do that, but that means backfitting a lot of stuff, so that's quite expensive. That brings us then to the potential about, how could you do this better in open source? So one idea is that you could have some sort of official, code line, or project supported code line somewhere, and that you get the interested parties to kind of do, maybe create a consortium or some sort of structure to do this together and share some of the cost. There's a lot of discussion around this going on for various projects and so on in Linaro, in the AGL, automotive grade Linux and so on. The biggest thing is you need to have somebody to blame if something goes wrong. And I mean, that's one of the main purposes of certification, really. So this is interesting, this is evolving. I don't know whether open source can play a role in there, but we're going to try. So let's just look at some examples of vendors who are using Xen in embedded as well as in automotive, and a quick demo and then close. So one of the vendors we have is Dernaworks. They started out as a small consulting company in the US. They're now maintaining 3 Xen distros. They used to have different names, but they've kind of rebranded them now together. There's like Virtuosity. There's Virtuosity for NXP and for Xilinx. Their core Virtuosity product is actually safety certified to various different standards. It's quite a long list down there. There is a company called Starlab. They're also going through that whole certification process right now. And then we have a few, that means that we actually know this stuff can be certified, right? It's doable at some reasonable cost. Those companies aren't huge, so you can do it. And then there's a number of others who play in that space too. Automotive, it gets even more interesting. So there is a company called GlobalLogic. They're tier 2 automotive OEM. They have a product based on Xen, done some contributions over the years. Right now they're very focused on bringing some of the stuff to market. They have a competitor called EPAM. It's quite similar what they're doing. I like EPAM more because they're a lot more actively engaged in the community, and they have some interesting features where they look at the sort of cloud automotive interface. I'm going to show you a demo quickly, and then we know that LG Electronics, Bosch, and a couple of others are playing with this whole stuff too. So demo, so those who are not going to be there, who are not here, they can see that demo by going to the link. I'm just going to try and play this now and see what happens.
The Internet of Transportation is becoming a reality, and soon, individual vehicles will become a part of this Internet. Vehicles need to keep up with the latest safety standards and regulations, but combining Internet-enabled software with mission-critical functions on the same platform creates quite a challenge for the industry. EPAM's Cloud Fusion platform is a unique solution that solves this challenge. It includes hardware isolation enabled by virtualization, rapid services deployment using containers, and end-to-end security for full cloud integration. With the EPAM Cloud Fusion platform, traditional in-car software stacks run on independent hardware using a special virtual machine dedicated to cloud-managed, dynamically deployed services. The instrument cluster, running a custom Linux instance, implements some basic vehicle functions. In-vehicle infotainment, based on HEL IVI, provides user applications and media features. The Fusion virtual machine is sandboxed from hardware and can interact with the rest of the system using an OEM-managed set of restricted APIs. Each cloud service is deployed to the virtual machine in a container. Deployed services cannot interfere with other processes. In this demo, the cloud service collects telematics data from the vehicle. Using a micro-service-based architecture, part of the cloud application is deployed inside of the Fusion container. Importantly, deployment of the app does not require any prior integration with the car OEM or Tier 1. To demonstrate the simplicity of the deployment, we'll enable some new features in the cloud application: fuel consumption, engine RPM, and gear settings. In this scenario, only some of the desired features are available from the in-car applications. Via a web application interface, the vehicle part of the application is updated separately, and new in-vehicle functions are enabled. Notice that the rest of the system operation is not interrupted during the service update. Even if the update fails or crashes or is otherwise unable to run, operation of the critical system is not affected due to the isolation of the Fusion virtual machine. After the vehicle service finishes updating, we see that new functions have been enabled in the vehicle. Fusion is based on open source software technologies. With Fusion, new automotive...
Okay, that's enough. Anyway, so you get the idea, and it's actually a really interesting use case. So looking at this diagram, that was the diagram we kind of saw earlier, but what's interesting again is that they're actually using some of these driver, rather than having specific drivers in separate virtual machines, they kind of split them up. They have the drivers for one application, in a different VM, and they're sort of cutting some corners there. But it's basically the same concept. So just to summarize, why is Xen really interesting in this space? As I said earlier, we're not really pushing it, haven't really started to push this very hard, because at the end of the day, this just happened. But after really 2 years of watching this, there's really something there which is worth building on. So, it's quite a flexible platform. It's used in a lot of different market environments. It's apparently relatively easy to port to new environments, otherwise we wouldn't see an explosion of so many different products. It's highly customizable, and part of it is also relatively easy to develop new drivers. There's quite a lot of security and resilience functionality there. Obviously, if we ever want automotive to become interesting, we're going to have to deal with the functional safety aspect. We're kind of looking at ways now how this could potentially be done. It's going to be a hard nut to crack. It's not going to be quick, but a lot of other projects are currently looking at the same thing. Linux has to solve this somehow for automotive-grade Linux. There's a lot of other projects which have to kind of help solve this, and we're starting to work together. There's a couple of challenges really which we're looking at. So we have a lot of different I/O drivers, some of them not open source, so we've been working with some of the vendors to standardize on some of the protocols. The same is happening around GPU virtualization. We're looking at maybe a more minimal DOM 0, like maybe we can use some sort of RTOS for that. That would be interesting. And testing has been a surprising challenge for embedded as well. So again, there we've been working, for example, we've been working with Renesas now to get some of the our car gen boards into a server chassis with some management functions such that we can actually deal with this in the same way as with other hardware. And hopefully some of the hardware specs for that will go open source, and then we can do the same for some other similar kind of, boards in the similar form factors. And that's really it for me today. If you have questions, we do have some time, do we? Yeah. You stressed me. I could have talked for a little bit longer. Never mind. There was a question up there. Was it you? Ah. Well, I think at the end of the day, it comes down to, I'm not telling you have, so the question was when to not use Xen. I think it ultimately depends on your use case and preferences, right? So if you look at Xen today, it's a lot more complicated in many ways than, for example, KVM. We've been hurting from that a little bit in the traditional server virtualization space because KVM is a lot easier to use. So I think, really, if you want to have simplicity and kind of maybe more ease of use, then maybe there's better competitors. If you're looking at some more complex stuff where you want to plug things together and you're actually okay with taking the overhead of the extra complexity, that's probably for you, right?
I do have a question. What about Intel support? Do you see Intel embedded is not so strong, but maybe in the industrial areas too?
Okay, so the question was around Intel support, and particularly maybe in some industrial areas, in industrial, and I guess there's a lot of these, how do I call it, plug computers, kind of this Intel in use. So there is some momentum there. I have two startups who are working on a product in this space and are probably going to use Intel architecture first to push into that market. There's probably going to be a container element in it as well. It is a lot more challenging I think anything which will require safety certification, it's a no-go area, at least for Xen, because the code base is a lot bigger. The ARM port is around, depending on how much you use or not, between 20 or 30,000 lines of code. The x86 stuff is a lot more, and quite often you need to use QEMU as well, right? So that's obviously a barrier, but I think in some market segments, it's definitely a possibility.
So you're saying those companies who succeeded in safety certification, they did it for art?
So the question was the companies who did the safety certification for
did they succeed? Sorry.
Who succeeded? They did it for. Actually, I think so. DernerWorks, I believe, did it both for ARM and x86, but the x86 configuration would have to be very cut down and constrained, right? Because otherwise it would be too cost intensive. And particularly in that, today we have like PD, you have to forget, right? I think it might become, HVM, then you have to deal with the QEMU aspect. I don't know, how you deal with this. You will probably have to use a QEMU and pretty much take everything out which Xen doesn't need. It's actually a lot, there's only very little Xen actually needs. But then you have to maintain that fork, right? Maybe PVH is actually, when this comes more widely used, that's sort of probably the interesting route to take. Yeah. Yeah, so power management is a really interesting challenge in this space right now. So this is something, so the question was, if you have drivers in different VMs, there are, properties like, power management which could cause problems, and you need to kind of address this. So, in fact, there's a really interesting story around this. So, I met some of the Xilinx guys who have their, distro, which have a Xen-based distro. Actually, we talked to them, I think in 2015. They invited me to an event, requested a meeting, asked a lot of questions about Xen. 2 years later, I didn't hear anything. They launched a product, and it was apparently quite successful. A lot of their users use it. But one of the things they have come across is exactly this whole issue with power management and stuff like that. But not only in the context of disaggregating drivers, but also higher up when you look at workloads. So on a driver side, you could focus on a number of operating systems which you allow, and you can plumb some functionality in there such that kind of gets coordinated. But what happens even further up the stack, right? If I look at this Xilinx Xen-based product, they have something called bare metal VMs, which are almost like traditional ROM images with a support library, and you just can bang, one of these old images into a VM, and they offer that, and lots of people use it. And then they have support for different RTOSes as well. But then you start, unless you have all the power management and all the sort of heterogeneous kind of coordination, it's not just about power management, there are other properties as well, then you're going to start to get into trouble. And I see some momentum building in this area to start resolving some of these problems. We're out of time apparently, so All right, and then my colleague here will follow up afterwards. So find me afterwards or at the Xen booth if you have questions.